He completed his diploma thesis at the Institute for Applied Photophysics at Dresden University in the field of ultra-short laser spectroscopy. Afterwards, he worked for 1 year on inorganic electronics and light projection devices, and while working on his PhD, he conducted intensive research on the application of doped charge transport layers to OLEDs. That brings us to this topic, which led him to found NOVALED, a company specializing in OLED technologies and materials also. Due to his knowledge of doped charge transport layers, he was a key inventor of NOVALED's PIN OLED technology. He worked for several years on NOVALED's technical director and CTO, and has been NOVALED's chief scientific officer since 2010.
Yes. Thank you very much. Dear ladies and gentlemen, welcome, and I'm glad that I was asked to present you something about OLED and the use of OLED in displays and other applications. And since you're mostly, as I'm most informed, electrical engineering, it's more a generic overview talk about what can you do with organic LEDs or organic electronic in general, because we as NOVALED, we are focusing more on the chemistry and physics part, so we don't have so much electrical engineering side, but I think it will help you to make your tour to the IFA. If you haven't done this, you will see lots of OLED displays, and I give you some more input on what you should look at and what is the potential and benefits of organic LEDs. So the outline of my talk, that is, I will first focus a little bit more on OLEDs and what is an OLED and what is organic electronics, before I enter a chapter about OLED display applications, and followed by some words about our specific technology. We didn't invent the OLED, but we have, let's say, at least one important technology brick brought to the OLED technology area, which we call the beer end or doping technology. And last but not least, I will highlight further application areas of the future of organic materials in electronic and optoelectronic devices. So this slide is pretty simple. This is an OLED. Basically, an OLED is an organic LED. LED stands for light emitting diode, and the O stands for organic. This organic, as opposing the classical semiconductor area, which use inorganic materials, is very important because it has different conclusions. One of this is that you can make every organic electronic device, including OLED, relatively easy on large area. The inorganic semiconductor had always the problem that they have to grow crystals. This was, by the way, the problem why we haven't haven't seen blue LED for over a decade or so. And in the 80s you could buy green LEDs en masse, but no blue LED. And just in the beginning 90s, the GR inventors invented or solved the problem of growing blue emitting crystals on silicon or on sapphire substrate at this time. And this problem is not existing for organic semiconductors because the organic matter, the semiconductor nature, comes more from a molecule. So you can just put the molecules like sand or so on substrate, and they have semiconductor properties, if the molecule has semiconductor properties. So it can easily be grown, in addition at low temperature. But the setup of an organic LED is very similar to an LED. What you always need to create light is you need to apply voltage by an anode and a cathode contact, and between you have the semiconductor layers. One of these layers, here sketched yellow, needs to create the light, and the light is created by the process that you apply voltage to the cathode and anode. Then charges are ejected, holes and electrons. They meet in this light emitting zone, the yellow zone, recombine to excitons that are excited states, and this decay of the excited states leads to an emission of photons for certain materials. For most probably of materials, it's not leading to photons, it's leading to heat, but for some materials it leads to photons. That's the light creation. But if now we put the emission zone directly next to the contacts, you would see that the light is dim and it's not very efficient. You waste a lot of electrons, so you have to put something in between, something less conductive, and that are the transport layers, one for electrons and one for holes. That's, by the way, the area where NOVALED is more engaged, as I will show later on. So this transport layer serves the function of injecting the charge carriers and leading them to the emission layer. I will come back to benefits of OLED in view of displays on a later slide. For some of you who have studied or heard something about chemistry, the most simple organic semiconductor is the benzene ring. Benzene is basically 6 carbon atoms and some hydrogen connected to this, and these carbon atoms bond together by pi bonds. So forms a so-called pi electron system, and if you have this ring of the 6 carbon, they are delocalized. So this is the single molecular picture. This is the, let's say, the single atom picture. This is the molecular picture. The p electrons are localized over the ring, and this are delocalized over the ring, and this delocalization leads to a level split between the highest occupied level and the lowest unoccupied level, similarity to the valence and conduction band in semiconductors, and this makes a semiconductor. If you have a band gap or a gap, you have a semiconductor. We know also these materials from maybe, let's say, applications. If you buy dyes for painting your wall or paintings of these kind of signs, these are organic semiconductors usually because they are in most cases also very colorful, or you drink them in such fancy sports drinks also which have odd colors. That's usually organic semiconductors involved. But let's say in a non-dissolved form, they form these kind of powders. That's what we as NOVALED, for example, provide to our customers, that are powders of this material. And if you put them in certain solutions, they get dissolved. But in our kind of OLED technology, we use vacuum coating to make the LED display. So we put these powders in the vacuum system, heat them, and they are evaporated, so we don't need to dissolve them. But that's where you know organic semiconductor from. And the next slide shows you our view on the whole area of organic electronics. As the most interesting today here at the IFA and in this conference are displays, so you can use organic LEDs to make displays. As you will see later, we have lots of mobile and smartphone displays already on the market, and first TV products are sold, like this 11-inch Sony some years ago, 2 years ago, but now we see more and more 55-inch OLED demonstrators, which should be installed later this year or beginning of next year. The second market for us is OLED lighting. Yeah? You can use the OLED to create light, which is good for display, but if you just make it to create light to illuminate the room also, we call it lighting, or if you create light to make signs, we call it signage, so that's kind of similar. And this market is also starting now. You see first design luminaires popping up. They are quite expensive and not really illuminating a full room like this, but it's the first step into an OLED lighting future. And the third market is, this is a little bit maybe a surprise to you, is organic photovoltaics, which is actually from a physics standpoint not a big surprise, because the OLED is creating light out of electricity, and the OPV, the photovoltaic application, is the other way around. We absorb light and create electricity. It works partially with similar design and materials, and so we are also engaged in this market. These three markets are more optoelectronic market, and the fourth market is the more electronic area, which we call the real organic electronic, which is consists of organic circuitries with CMOS type of organic transistors, synthetic transistors. You can make memory out of organic materials, RFID tags, batteries. And one of the first examples is here an e-reader from the Dresden-based or UK and Dresden-based company Plastic Logic, which is producing e-reader using organic transistors as backplane, and then the classical e-paper, e-ink technology as frontplane for the information creation. So this brings me to this chapter of OLED display application. So what is the main difference from the construction between an OLED display and an LCD, and why do people like Samsung and LG engage seriously in OLED TV? And the answer is here on this slide. One of the answers, there are several answers. One of the answers on this slide is just much more simple to make an OLED TV display. Therefore, an LCD display, you need liquid crystal, which is actually the switching element that creates the information. But you need to put it on glass. Okay, fine. You need to put two polarizers around this. That's already quite a bit. You need color filters in addition, and you need a backlight. And the backlight itself is also complex. It was based on fluorescent tubes in the previous times. Now it's based almost 100% on LED backlights. But you need diffusers, you need light guides, you need optical means to bring the light towards the viewer. And OLED display in contrast is pretty simple. It still has the organic layers, that's the OLED basically, what we have shown on the previous one of the previous slides. But then you have to put the OLED material on something, so you put it on glass today, or you put it on flexible substrate in the future. You also need a TFT to make a display, because you have also millions of pixels. And if you have millions of pixels, you need this active matrix kind of backplane. And you need one polarizer, because otherwise your OLED would look like a mirror, which is nice for lighting applications, by the way. You can coat your mirror with OLED materials. You can switch it off, you see yourself, you switch it on, you can use it as a lamp. But that's nothing for display, because display needs contrast, and therefore you have this ambient light polarizer to put on top. But basically the almost complete assembly of an LCD TV is circumvented in the OLED case. So from this perspective, it's much more simplified display production. There's no backlight required, which is lower cost, which should lead at the end to a lower cost at similar scale. And if you produce 55-inch OLED TV on the same scale per month as LCD, OLED will be cheaper. And very important, let's say, I don't know if it's a benefit or so, but it's very important to know that today's LCD TV manufacturer will be the OLED manufacturer of tomorrow, because the backplane is still needed and still basically the same from the principle. And the backplane in an LCD TV or LCD panel production makes more than half of the cost. And you can reuse this production. So what you see today in Korea or also in Japan, that old LCD fabs are converted into OLED fabs. So, and that led to the, let's say, fact that at the CES, so this slide was done before the IFA, so I have CES pictures from January, and a list here of applications which are shown or already on the market. Most dominantly is the smartphone success of mainly Samsung. So if you go to the Samsung booth today, you see the Note 2, you see the Galaxy S3, always OLED displays. So from the small to medium-sized display, these guys are using OLED, and then Nokia is using Samsung displays and others as well. LG is producing some mobile phones and also producing OLED displays for smartphones. The next step is tablets. So Samsung has a 7.7 Galaxy or an iPad. Toshiba has on its booth a 7.7 OLED display. I will explain you later that they made a mistake in the, let's say, how they described this on their booth. And TVs, as you can see, if you go to the two halls of LG and Samsung, you see huge installations of OLED 55-inch TV. And you can experience the difference. I will come back to the advantages of OLED TV versus LCD TV later, but this is the most electronics slide I have in my talk. That is the construction of an AM OLED display. Pixel circuitry. As I said before, the OLED display is an active matrix display. There are, or there have been, OLED passive matrix display as well. They are produced in Taiwan for gadgets like watches and let's say a secondary display in mobile phones. You maybe remember this clamshell mobile phones which almost disappeared over the last 3 years. As I realize now, they had many OLED displays and so on. These are done, these low information content displays are done by passive matrix OLED display, but most or any smartphone, everything beyond QVGA is based on active matrix OLED. And this active matrix pixel looks similar to LCD, but there are also differences. The main difference is that the OLED is a self-emitting element, and if you emit something, you need energy, and if you need energy, you need current and voltage. So you control the OLED pixel brightness by the current. So you have to control the current that you do by, let's say, control or driving TFT, which is connected in series to the OLED between the VDD supply voltage for the whole panel and the ground connection for the whole panel. For every pixel the same. And that tells you already that this driving TFT has to drive a lot of current if the pixel is on, but it also tells you that if the pixel is off, you just close this driving TFT and there's no power consumption of this pixel. That's a nice thing, because if you have, let's say if you look Star Wars, you consume suddenly 1/100 of the power consumption of an LCD. I mean, also LCD are doing pretty much things to, let's say, reduce the power consumption then, but it's very simple. You just switch the pixel on, off, and then you don't consume any power anymore. And the pixel is very black, by the way. black level is a very good advantage of AMOLED displays. And in order to control this TFT, you need again a storage capacitor. The storage capacitor status, so the voltage or the capacity of this, or the density of charge carriers on the storage capacitor determines how the gate voltage of the drive TFT, and the gate voltage of the drive TFT determines the current that flows through this drive TFT. And in order to control now let's say the status of the storage capacitance, which has to be changed every frame time, I mean, depending on pixel content, there's a certain current flow at this frame time, and if the next frame comes, you have to go to a different capacity. And this is done by this switching transistor, which is here. The switching transistor for one line is switched on by the scan line, and the data for this row is coming to this contact and is written into the storage capacitors. And then you switch off the scan line where you have been and go to the next scan line, so you scan the same thing as a TV display, CRT or any other active matrix display, and then this TFT is switched off and the storage capacitor unloads over the gate voltage of the drive transistor and keeps the current in this frame time constant. So the OLED is basically always on. Yeah. And the pixel look, or the display looks then like this. This is a QVGA AMOLED display demonstrator which we have done together with University of Stuttgart, Professor Frühauf's group, and also limits the resolution here. If you want to, let's say, increase the resolution for a given display size, you have to make these openings in the mask very small. This is challenging, or if you want to go to, let's say, from smartphone production to really generation 8 display production, you have to increase the size, the sheer size of this mask towards 2 by 2 meter, and this is also challenging. But this is something where companies like Samsung and LG are working on. And the consequence of all this is, let's say, that OLED has several benefits over LCD. Basically, what I always tell people, if they ask me in one sentence, what is an OLED display? What makes an OLED display special? I say it's the combination of the best properties of LCD, high resolution, and the best properties of plasma, self-emitting, direct-emitting color, and so on. And this is basically the OLED display. It's the best of both worlds without the disadvantages. At least there's not big disadvantages known to me in comparison to the other technologies. So therefore, performance benefits are, you can expect more saturated color because you create the colors directly. More saturated colors also lead, interestingly, to higher brightness, higher perceived brightness by the Helmholtz-Kohlrausch effect. An OLED display with 200 candela per square meter screen brightness seems to be brighter than 250, 300 candela per square meter LCD just because of more saturated color. You have a much better dynamic range. Now we have a problem with the measurement of contrast of today's LCD. You get, I mean, the LCD that you buy today in stores have 170-degree contrast ratio. You think, yeah, well, I mean, I don't sit 85-degree off access to my LCD, so why do I need, how can it be better than this? And the reason is that this specification of today's contrast is a little bit odd because at this viewing angle you have to be above a contrast ratio of 10 to 1, which is the case for LCD. If you have a 170-degree viewing angle LCD, it has a contrast ratio of more than 10 to 1 under sharp angle, but you're used to, when you look front on the display, you're used to much higher contrast. And OLED has this contrast, this high contrast, also under very small and wide viewing angle. And that's a very big benefit. Also, the contrast in low brightness situation is much enhanced. Yeah? This usually, if you look at a movie on your screen, you are not at about 50% screen brightness, you are playing around 0 and 10 and 20%. And here you keep your brilliant contrast ratios. That's something which is really a huge benefit, which can be just perceived by eyes. You can go to the booth there and see how vivid the colors in the pictures are. Power consumption is a benefit because if the pixel is off, it's off. If the pixel is on, it consumes power, but not if it's off. And they are extremely thin, so the 55-inch TV display demonstrators and displays shown by LG are 4 mm thick, which is amazing thin. And the OLED displays, which are inside the smartphones, probably 1 mm thick or so, which allows basically that you can make and this is a Galaxy S2, but if you go to a Note, which is a huge mobile phone, if I go to my wife and say, I have a 5.5-inch display, she tells you, you're crazy, how you will transport this. But if you touch it, you see it's just 7, 8 mm thick, then the volume is the same, the weight is much less than an iPhone. So this is okay. Yeah? If you're getting bigger, you have to also get thinner to keep the volume under control. This you can do with OLED. And it's also perfect for 3D because it's very fast. So the switching time of an OLED is much faster, factor 100,000 or 10,000 in comparison to LCD. So you can really switch extremely fast. Not as fast as you can switch an inorganic LED because the mobility of the organics is a bit slower, but much faster than LCD. The reason is in the LCD you really move matter. Yeah, you move these long molecules, you change by voltage, the organ. But here you just inject electrons and holes that are very lightweight matter, so it's fast. So that leads to the fact that you see this here. I just downloaded these pictures. This is one-to-one the 55-inch LG that you can see in all, whatever, 17 or so. And you see the Galaxy S3 and the Note and so on, more and more in markets. So what's now NOVALED doing here? NOVALED is a key material supplier and IP holder, so we are more a chemistry physics company. So we supply what's inside the OLEDs. And our technology that's shown here, this is the first picture basically again, that we put certain additives, which we call dopants, into the transport layers. We develop and market the dopants. We also develop and market the transport material. Dopants are used, let's say, to 1-2% by volume. They are very expensive. They are edgy chemistry-wise. We have lots of chemists in our company which day-to-day work on new synthesis procedures. I'm physicist, so for me it's secrets. But let's say they are cooking there. They come back to me and say, I need much more time, much more resources to develop these strange molecules which you want to have. So they will be expensive at the end, but these fancy molecules, they are just used as a small amount dopant additives. So that's okay then for our customers that they pay premium basically to really improve their display functionality quite a bit. We don't work on emitting materials, so we are not the guys making color, bringing color to our world, but we bring the charges towards the regions where the color is created. And we not only do chemistry, we also do develop structures based on this approach. The real OLED structure is a little bit more complex. I have a slide later on. And we optimize that, we make IP around this, so we try to, let's say, protect our know-how and our results by intellectual property. The main benefit of this doping technology is that you reduce the operating voltage, because usually these transport materials without the dopants, they are fairly less conductive in comparison to inorganic semiconductors. So you have a voltage drop there, but you don't want to have a voltage drop in the transport layers, you want to have the voltage drop in the emission layer where it creates light. So usually an OLED without doping functions at maybe above 4 or 5 volts, and we can make OLEDs which are below 3 volts. Usually we work between 3 and 4 volts. So we really lower the operating voltage of the OLED, and by this, as you will see in one of my later slides, we enhance the power efficacy. That means how much electrical energy we have to supply to the OLED to achieve a certain light output. I skip the other benefits because they are not so important. Let's say some physics and chemistry mixture here. This lowering of the operating voltage is done by this connectivity enhancement, and this view graph shows it very simplistically. You make a layer out of, let's say, 98% of this and 2% of this molecule. This is a matrix. It transports holes, and this is a dopant which puts an additional hole on the matrix, and these additional holes, they are leading to a conductivity enhancement. So if you have 1% doping, you have 10 to minus 5 to 10 to minus 6 Siemens per centimeter, and if you increase to 6 or 7 molecule percent, volume percent, then you have 1 to minus 5. And if you don't use doping, you are at 10 to minus 10 Siemens per centimeter. So that's really low. I don't show it here on this slide. This slide also tells the physics among you that, let's say, the activation energy follows quite similar rules than in inorganic semiconductor physics, where doping is also used. And now chemistry, why we have so much chemists, is that the materials have to have additional specs than the pure performance specs. The evaporation temperature of these materials, they have to be in a reasonable range, 150 degrees Celsius to 400 degrees Celsius. The vapor pressure must be low. If it would be high, it would lead to cross-contamination, so that over time you produce a weak or 2 week, and then over time our dopants diffuse to other parts of the OLED and destroy the OLED there. That would not work, and also you have to avoid that the dopants diffuse in the matrix at elevated temperature. If you think about car application or even at let's say consumer applications, if our additives, our dopants would diffuse around in the OLED, they would also destroy the functionality of the OLED. So therefore, we do develop lots of materials. That's the message of this slide. Don't want to go too much into details. One of the advantages of our technology is that it can be integrated on many kind of different substrates and structures, so we ease our customers to make transparent OLEDs, for example, where you have on both sides a transparent contact based on indium tin oxide, for example, or based on thin metals. We can put OLED on printed ITO or printed metal. So there's a first step towards printing OLEDs, which will also be done in the future. And we can also put OLED on steel substrate or other metal substrates, as we have shown in cooperation with ArcelorMittal. So therefore, let's say we founded NOVALED 2001, not me alone, but together with 2 other fellows, and we are a classical spin-off, a kind of American model of a spin-off company from university at Fraunhofer, and brought this to the market. 2003 we got our first financing round by different venture capital financing at Thomson. At that time, when they still have had the mission to produce OLED displays as well. And in the meantime, we collected more venture financing. We have 130, 140 employees located in Dresden. We've been profitable in last year with 17.4 million euros revenue and have more than 500 patents and patent applications. I think it's 520 or 530 now. And we have presence in Seoul and in Tokyo in the meantime, because the display market, as you all know, are mainly located in Asia. Our business model is, as I think I explained before, we develop materials, we develop IP, and then we subcontract production of the materials, we get this back, and we sell the materials and our technology to our customers in the display and lighting area. So that's on the display. Now other organic electronic applications, I showed it a little bit before, but this is our organic electronic opportunity. Let's say starting from smartphones, tablets, that's where we live from today, that's where we make our revenues from. And we are looking very positively forward to TV. In 2018, Display Search Market Forecast also is predicting that the OLED display makes 26 billion US dollars revenue, so it's should be at that time 30%, maybe a little bit less, of the whole flat panel display market. That's quite substantial. And afterwards there will be the lighting opportunity, which is, let's say, I will explain something about lighting in the next slides. And then comes the flexible opportunity. I'm very much convinced that the OLED applications will be put on flexible substrate. There is a challenge in encapsulation. Organic matter is usually not stable versus water and oxygen. So we have to block the penetration of these two, let's say, ingredients to flexible substrates, but this will be manageable. And then we have flexible displays, flexible lighting, and the next opportunity is this organic photovoltaic, organic electronics in the future. So let's say also for OLED display it's important to be green and to consume less power. But there is, let's say, in a display you have many power losses. You have power loss in the backplane, you have power loss in the electronics, you have power loss in the OLED if it's an OLED display. So if you improve the power efficacy of the OLED, you just work on one power consumption ingredient. But for OLED lighting, power efficacy of the OLED is utmost important. Yeah, the OLED panel that you produce to create light has to be very power efficient. You recognize that the incandescent bulb is banned since today. Basically in Germany you don't get any 25 watt incandescent bulb, and an incandescent bulb is banned because it has just 10 to 15 lumen per watt power efficiency. And so you have to be way above with new lighting technologies as 15 lumen per watt, otherwise you will be banned according to EU guidelines. So the power efficacy is basically determined by 4 main factors. The first factor is balance factor B, which is not so important because if you do a good OLED design, you can optimize that. The second factor is where we play with our doping technology. That's the inverse operating voltage. As smaller the voltage is, the bigger is the power efficiency for the same light output logically. So our doping technology directly reduces the operating voltage. The second main factor is what we call here the recombination efficiency. That's the question, how much photons do you create out of one injected electron? And many of the today's used emitter materials, the materials are not capable of converting more than every 4th electron into one photon. so they have an upper limit of 25% internal recombination efficiency. Now and in the future, people will use more and more so-called phosphorescent materials which have not this limitation and can, in theory, reach 100% internal recombination efficiency. And the last factor is what we call the optical or the outcoupling efficiency. The reason is that you, the observer for any light, if it's display or lighting, you sit in air. Yeah, we live in air. We don't live underwater, we live in air. Air has a refractive index of 1. Glass has a reflective index of 1.5 around, and organic matter has reflective indices of 1.7 to 1.9. And the consequence of this is, if you create a photon inside the semiconductor, which is the case because there the excitons meet, it cannot escape easily towards air because there is this change in index of refraction, and if you have a flat surface, you undergo total internal reflection. And by this, the OLED has just, let's say, outcoupling efficiency, and this is just shown on the next slide. The standard OLED is just coupling out 20-25% of the light that is internally created comes out. The rest gets absorbed and is converted into heat. So therefore, also today's OLEDs are still, let's say, generating quite some heat. This is what happens in this case. By the way, LEDs, inorganic LEDs, have a much bigger problem here. They have a refractive index of 3.5, and only 2 to 3% of the light is coupled out. That's the reason, by the way, that LEDs are usually made in chips, very small size. These chips are complex structured like pyramids, and this pyramid structuring helps light to couple out by multi-reflection, and therefore the LED is always a point source of light. Whereas an organic LED, you can first you can process it on large area, and secondly, it's much easier to couple the light out. But still, I mean, 75% is trapped inside the OLED. That's not what we want. We want to get this light out. So therefore, also NOVALED and many other companies are working on improvement of this light out coupling. I will show one example how we improved here the light out coupling to maybe around 40%. We think the practical limit is around 70%. Practical means we can definitely find physical ways to couple 90-95% of the light out, but they will not be scalable and they will be very expensive. And what we need at the end, if you want to make lighting or display, if you have a 55-inch display, you need to couple the light out on big areas. So it needs to be scalable and it needs to be cheap per area. Then we talk here about $10 or so what the outcoupling per area per square meter can cost. So therefore there's a certain practical limit which is determined by business arithmetics. So this outcoupling is shown on the next slide. How do we achieve this, let's say, 40% outcoupling or 45% outcoupling? The left picture here is a normal OLED, the standard OLED with 20-25% outcoupling. The light is created inside the organic LED and this refractive index 1.7, and it's partially trapped here. A part of the light is put into or transferred into the substrate, which has 1.5, it's glass, let's assume, and also is trapped here, and just this tiny little amount of light goes out. What we can do first is we can apply external outcoupling means, like micro-lens foils or so, which we put on the backside of the substrate, so the OLED on one side and the outcoupling, external outcoupling on the other side, and now you attack this, let's say, these glass modes, and they get a higher chance to be coupled out because of this dome structure of the micro lenses. The internal index or this internal reflection is minimized and more light comes out. Maybe this improves to a certain percent in outcoupling efficiency, but the remaining OLED light here, which is lost over time, that is still trapped. So we have to put something inside the OLED, some kind of internal outcoupling technology or means to also scatter first the OLED light into the substrate light, and then we have the micro-lens array and put the substrate into the air modes where the observer stands. We can achieve 40%. Now it's a little bit more complex because if you put something in the OLED and this should couple light out, it needs to be three-dimensionally structured, so it needs to be rough or kind of bubbles in high index materials and so on. And this usually creates rough surfaces, and then the OLED usually has shorts. After some time at least, because the OLED is a semiconductor device which is just 100, 200, 300 nanometer thick, so it's around about 1/10 of an LCD thickness, and therefore the danger for electrical shorts is higher. So we managed in NOVALED to create a little bit by coincidence as well, a molecule or material which we call here the net 61, which forms intrinsically after evaporation. It forms kind of rough layers, but rough in the right sense. So miraculously, we can put this layer into the OLED close to the cathode, and we don't get any short, and it works on large area. So this is very nice, and then we make an OLED having this external outcoupling, internal outcoupling, lots of organic layers, so in reality it's much more than 3, it's many, and we can reach up to 60 lumen watt. I think this is the main important measure here, this 60. The other thing we can forget for our purpose today. And we can make this on large areas, so we have used this for demonstrators which are some square centimeter in size, but if you manage 4 square centimeter, you also manage 100 square centimeter. The scaling then is becoming easy. And the lifetime of this OLED, done in our lab, but already having this larger size, is in the range of 100,000 hours until brightness is 50%, so we call this T50. And for T70, so brightness 70%, it's 27,000 hours. That is 10 years or 2.7 years constant operation of a light source, which you don't switch on all the time. And that's also the ballpark number where today's TV display applications are probably in respect to lifetime. And you have plenty of demonstrators if you go, I mean, you don't go to IFA for seeing lighting demonstrators, but you have to go to Frankfurt to the light show there, which is every 2 years, and you see lots of OLED products and prototypes. And these are some of them from partners and customers of us. And this is one product we designed, and we also sell under the Laternity brand. So it uses 4 of these very flat OLED panels from a supplier, not produced by us. And it uses a carbon housing, very nice, high luxury. It's very expensive today because the production size of OLED panels for lighting is quite limited, so therefore the price is still expensive. So therefore we focus here first on designing in your market to, let's say, help supporting the OLED lighting market. Yeah, that's a summary. Our success has been recognized just briefly here. Last year we won the Zukunftspreis of the Deutsche Bundespräsident, which was very nice. At least the probably more capital maybe here is still on board. And so this brings me to the summary. So OLED displays undergo rapid growth currently in small to medium-sized applications. You see them everywhere here on this IFA. Also, OLED will change the TV display market. If you look at the Samsung and LG OLED display, they are marvelous in my view. Please check for yourself. And our offering in this market is that we sell materials and technologies for lighting display, and in future also for OLED. And I don't end any talk without thanking the financial funding which we received, because we are a startup company, we have been a startup company, we have been fast tremendous growth in the past years, which would not have been possible without funding from XNE, BMBF, BMWA, and also the European Union. And I also thank you for your attention.
Thank you very much. I'm especially happy to see that this activity is followed, especially in Germany, and that is successful, as my company has unfortunately decided to stop this development.
But you helped kick off NOVALED, so that's all.
So, other questions?
I have a question about the complexity of the outcoupling, light outcoupling. So you stated that it's quite simple to build a TV set with OLED because it's, well, basically 3 layers. So, but we had quite a few layers stacked on top on slide 26. So,
yeah.
Is there any contradiction, or is that impose new steps in the process?
No, let's say this stack here is a very complex stack. This is a demonstrator stack which we do for lighting demonstrators, which contains, I think, 12 layers, or even a little bit more, but this will not be produced. These are 3 OLEDs stacked on top of each other. In production, there will be 2 units stacked on top of each other. And then this is 2/3 of the complexity for lighting. The display stacks are less complex. One of the reasons is that you have 3 display stacks next to each other. So you have a red, a green, and a blue. And here in the lighting stacks, we have to combine, I didn't take time to explain this. You combine here the blue emission a green-orange emission and a more orange-red emission to create the right light. That makes it more complex, but you also have just this one stack. And if you look, let's say, if you allow me to comment a little bit, give you some guidance on the IFA. If you go around IFA, you see the LG OLED TV and you see the Samsung OLED TV. They are based on totally different constructions of the OLED. The Samsung one is an RGB side by side, so it's done by this masking. So it's very brilliant, very vivid. The LG is done by such a stack, probably also a 2-unit stack. I'm not allowed to comment on the exact nature of this of the construction, but it's a white OLED stack, and LG puts a color filter above this. So we have the color filter again, which we usually want to avoid in OLED, but I use this color filter. The color filter is WRGB. So if you go there, you see on one side you see WRGB, and this is because of the color filter, which has a wide area, so there's no absorbing line for the matrix behind is basically that most TV colors are non-saturated colors. So you leave one pixel open for making the white content, and then they have red, green, and blue pixel. So 4 side by side, or I think in a square, and they make them the saturated colors by mixing red, green, and blue. This is kind of compromise. They sell it as a big advantage, the first 4 pixel or 4 color TV. Better is the Samsung RGB approach from the color quality, but LG has it easier to produce because they don't have to mask this RGB pixel side by side. They make it more complex white pixel, but then they can let's say put the complexity of the color towards the color filters, which is a process they know from LED since many years. But it's a compromise because the power consumption goes down because you absorb part of the light in unwanted area. So you see the technology is still in a non-mature status, and there are still things to develop over time. I think on the long run, RGB direct creation will be the way to go.
Is there another short question asking for another short answer?
You have to ask me now because I unfortunately have to leave for time reasons, so you don't have time to ask me later.
Take the opportunity.
Could you comment on which effects limit the lifetime of the displays, especially when we want to have lighting and so on? Lifetime of the devices in terms of efficiency?
Exactly. I mean, what you do is you create light by the combination of electrons and holes. That means your device has to see lots of current. Right? If you want to create much light, you see lots of current. So this is a degradation factor. If then oxygen and water comes in addition, you have light, you have active chemical reagents, and you have also a certain kind of heat that destroys some molecules over time. This is basically the reason why lifetime is limited. Now, if you have less stress or less current, lifetime is longer. That means if you drive the OLED harder and brighter, lifetime is shorter. So we as a chemistry company, a material company, are constantly developing new materials. We do try to understand better the lifetime limited factors. We also are very engaged in understanding the OLED structure. Therefore, we make this technology development, because if we can somehow manage to, or if we can understand the degradation channels, we can manage to work around them in the design of the OLED. So this over time makes the OLED better and better and longer lifetime. It's definitely long enough for smartphones. They are sold since several years, and I didn't hear complaints about lifetime. TV is different because TV you don't replace every second year. You keep it longer in your home. You might also, I mean, not we don't know. I mean, we have no problem with our lifetime in the TV, I guess, for the whole life. But some other families do have problems with the lifetime of the TV, so they have to be constantly improved. As far as I know, the lifetime is considered good enough for starting TV business. And lighting is the same. If you can achieve the luminaire having 10,000 hours lifetime as a complete finished product, it's not only the OLED, it's also the connections, mechanical towards the contacts, then you start the market, and this is what you get as guarantee from Osram and Philips today, is around in the range of 10,000 hours lifetime guarantee. And this is much more than an incandescent bulb has 1,000 hours, and also LED packages, they are not so beyond 10,000 hours. And with this stack here, which we show here on the slide, we reached this 27,000 hours at T70, which is a good lifetime. Now it has to be transferred into real products, but this is good enough. We once made a lifetime record for a red OLED which lived 1 million hours lifetime until T50. That's 100 years. And then everybody says stop it, because people don't want to sell a product which lasts 100 years. Nobody wants to sell it anymore.
Okay, thank you very much again.